Okay, it's time to start looking at how to calculate the step responses. And the first point to note is that the input step is not a complex exponential. Therefore, we cannot use the idea of complex impedance and phasors to analyze the behavior of the circuit when it's presented with an input step. We have to go back to the original equations that specify the behavior of capacitors, inductors, and resistors in the time domain, and produce a series of simultaneous differential equations that have to be solved. This can get quite tiresome, but I'll try and point out a few shortcuts and easy ways to get to answers as we go through some of the more complex cases that we'll be looking at. In this video, I just wanted to show you an example of the solution using the simplest possible example, that of a zero-order system. Zero-order systems have no poles and no zeros, so they can conveniently be analysed as potential dividers, since that's all they are, and potential dividers just built using resistors. The example in the slide here has an input here at A, feeding into a potential divider in which both resistors are equal. And if both resistors are equal, then the output voltage here at B will just be half of the voltage at A. So I could write that at all times the voltage at B is equal to the voltage at A divided by 2. And if the voltage at A is a step going up to 1 volt at time t equals 0, then the voltage at B must be a step that goes up to half a volt at time t equals 0. And that is the step response of this circuit. Couldn't really be easier. In terms of the frequency response of this network, we can calculate that as well. H of omega would just be equal to, in this case, 1k over 1k plus 1k, which is a half, and it's independent of frequency. Now, when we're plotting frequency responses, we usually plot them with decibels on the y-axis. So if we were going to plot this as a frequency response, and we use log of frequency on the x-axis, so if we were going to plot this as a frequency response, we would want to express the 0.5 in dB. Well, that's just 20 times log of 10 of 0.5, which is minus 6.021. So that would be our frequency response of this network. Hopefully, this was very familiar to you. I just wanted to go through the technique again because we'll be applying it to some more complex networks in the next videos. Next time, we'll have a look at some first-order circuits. That's circuits with one pole in their frequency response.